Morning everyone. So we will continue our lecture for today. So although today's tutorial, but because we haven't really finished chapter 2 yet, we cannot start on the tutorial. So I replace it with lecture instead. Okay, so I understand last Monday lecture was a bit heavy, and actually today's lecture also dah a little bit heavy, should be heavier because last Monday you basically just you were introduced to the types of reactor, you were introduced to the design equation. However, what you learn in Monday is actually understanding. Okay, but today class, we will start applying what you have already learned or introduced in last Monday class. Okay, so I will go not so fast, I will go a little bit slow. Sebab tu I prefer that I do as many class as possible, so that each class I don't need to go too fast, so that your understanding should be better. Because reaction, as I told you, the subject, the course is really a building course, meaning if you are not able to understand the beginning, it gets actually harder and harder as it goes by, right? Okay, so just a little bit of short recap. Last Monday, we already learned the types of reactor as well as the design equation, meaning we learned that the three main reactors, batch, PFR, CSTR. Okay, so we learn to derive the design equation for these three reactors. Okay, so what we're going to do today is we are going to actually now design the reactors, or in simpler terms, we are trying to determine the volume for batch and the volume of the reactor for CSTR and PFR, and for batch reactor, we're talking about reaction time. Okay, however, today we will learn first on determining the volume of plug flow reactor and continuous stir tank reactor, meaning we will learn how to know the volume, to calculate the volume of a PFR and a volume of CSTR. Okay, lepas tu, we will first learn the single reactors, meaning we want to determine the volume of one CSTR or a volume of one PFR, meaning if I have a reaction, I can determine how big my reactors shall be, okay, for one PFR or one CSTR if we are using one reactor. Okay, once we understand the single reactor, we will go slightly harder as we will calculate when we have more than one reactors connected in series. So we will design, or we will calculate the volume. If let's say I have 2 reactors in series or 3 reactors in series, so on and so forth. So it becomes a little bit difficult because the equations will be slightly modified when we consider different kinds of arrangement of the reactor. Okay, but it's okay. We first start with designing volume of a single reactor. Okay, now for today's class, okay, we have to understand that designing the reactors, it must come with information. That means it comes with certain information, then only we will design the reactor. Okay, for today's scenario, or today, what I'm going to teach you, you have to assume, or not assume, it's a scenario of which, let's say, you have a new reaction, meaning let's say you're working in a plant, okay, they come up, or the chemist in the laboratory has discovered a new types of reaction or alternative types of reaction. Okay, so maybe because you change the raw material ke, or perhaps you change the parameters ke, so the chemist in the laboratory has discovered a new way of producing this chemical through a new reaction. Okay, so naturally, kalau it's in the lab, like I told you last Monday, they will definitely use a batch reactor. So maybe kalau small scale reaction, or you just want to start doing a new reaction, you want to understand the behavior, they will do it in a batch reactor in the lab. Okay, so in the lab, okay, let's say imagine you got a small batch reactor, they run the experiment, okay, then they will calculate the rate of reaction with each conversion, meaning katakan Dia said, if I want to achieve a 0% conversion, means no conversion, how much is the rate of reaction? So rate of reaction ni, I remember I told you, we will always talk in terms of minus RA. Minus R is rate of disappearance. A stands for the reactant A. So means they measure, okay, let's say conversion 0, how much is the rate of disappearance of A? So macam mana dikira? They measure concentration of A lah, means kat conversion 0, how much concentration of A per time. Okay, so they get minus RA for conversion 0%. Okay, ataupun 0 lah fraction. Then they do for 10% conversion, how much is the minus RA? 20%, 30%, so on and so forth until they get the complete table of information which conversion versus the minus RA. Okay, so you assume now the laboratory or the chemist has done this experiment in a batch reactor and they have produced to you this table of information. So from this table of information, which is conversion versus minus RA, as I told you, conversion, sometimes we will mention in terms of percentage. Okay, sometimes we mention in terms of fraction. In calculation, definitely we have to convert or change into fraction. Okay, so I have to keep reminding you. Okay, so sometimes they will tell you conversion is 80%. Tapi bila dalam penyiraan in the calculation, make sure you change that 80% to 0.8. Any percentage dalam penyiraan, you have to change into fraction. Okay, so come back to this. So imagine you got the table. X melawan minus RA, the information in the form of table, and the chemist provide you information and you're supposed to design or upscale the reactor into a continuous system. Ini kalau saya nak design PFR dan CSTR using this information, how big my reactor will be. Okay, so this is what we're going to learn today. Ada information dalam bentuk table ni, kita nak cari volume PFR dengan volume CSTR. We want to know how big my reactor should be. Okay, so you remember last Monday, we actually dah learn to elucidate or to determine the two design equation, one for CSTR and one for PFR. Okay, so the volume CSTR, okay, the formula is given as equals to FA naught X per minus RA, means the volume of CSTR equals to initial molar flow rate of A multiplied with conversion over the rate of disappearance of A. Meaning, okay, X dengan minus RA ni berkait, means at conversion 0.5. Let's say daripada table ni, kamu tengok, katakan conversion dia 50% ataupun 0.5, minus RA dia 0.25. Okay, so minus RA dengan conversion is related to one another, means different conversion, different minus RA. Okay, on the other hand, volume PFR is given as FA naught integration 0 to X dx per minus RA. So kalau kamu perasan, volume CSTR is easier to find sebab dia linear equation yang biasa. PFR ni susah sikit sebab dia melibatkan pengamiran. It involve an integration. Why the integration limit dia from 0 to X? Okay, ni pun kamu kena faham. Okay, you have to understand why the integration. If you have question boleh tanya. Tadi ada macam yang tu. Okay, so the integration is from 0 to X. Why 0 to X? Sebab dalam single, this is for single reactor. In one single PFR, the initial conversion mestilah 0, means pada asal. Is there any question from anyone? Firhat, ada soalan ke? Ataupun Firhat terbuka mikrofon? Okay, thank you Firhat. Right, so for PFR, why the bottom limit or the lower limit is 0? Sebab pada asal tindak balas dalam reactor PFR tu, for the single PFR, the small ataupun the early part of the reaction, conversion dia kosong, means no A has been converted yet. That's why it's from 0 to X. X is your final conversion lah, depending on your reaction. Okay, sebab kamu kena faham bottom limit dengan upper limit sebab nanti kita akan belajar reactor in series, more than one reactor. So you will then understand kenapa bottom limit dia kejap kosong, kejap bukan kosong. But for single PFR, the bottom limit integration dia mesti daripada kosong sebab waktu asal tindak balas no conversion has occurred yet, or means no A has been converted yet. Okay, 0x. Alright. Okay, so now okay, now we talk about the table first before I go further on the calculation. Okay, now that you understand how the equation is going to be used, we talk about the table first. Okay, information adalah bentuk table yang tadi saya kata dengan kamu, the one that I told you just now. The table can be in the form of X versus minus RA, meaning someone in the laboratory has already calculated for you. Untuk conversion kosong, berapa minus RA. Conversion 10%, berapa minus RA. 20% until 100%. Okay. This table of information can also be converted into a plot, which we call it as Levenspier plot. Okay, so Levenspier plot ni beza dia daripada table from the table information we can use to plot the Levenspier plot. However, Levenspier plot tu, okay, kamu tahu kalau kita nak plot graph, kita kena ada data y-axis, x-axis. Like setiap titik tu kena memerlukan data paksi y, paksi x. Okay, the data or the plot for x-axis is conversion. Okay, means daripada table tu, conversion tu kamu akan guna untuk plot data paksi x. However, paksi y, okay, for the paksi y data, instead of using minus RA, we will use 1 per minus RA. Maksudnya daripada data table tu, yang data minus RA tu, kita kena reciprocalkan ataupun kita satu perkan minus RA to get the data for the y-axis. So the data will be 1 per minus RA versus X. So bayangkan dapat table ni. So katakan pada at 0 conversion, the minus RA was 0.45. So 1 per minus RA becomes 2.22. Kamu perkan jaja 1 per 0.45 dapat 2.22. Do for the rest of the table information. Then kamu use the data X and 1 per minus RA to plot the plot. We call it Levenspier plot. Okay, so I'm sure you might ask, kalau dah ada table, dah boleh guna table, kenapa nak guna plot? Okay. So, actually, both table and plot can be used to find the volume. Okay. So, why do we want to use plot? Okay. Actually, using the plot will be an easier way to calculate, or I can say that it's easier for you to imagine the calculation when you use the Levenspier plot. Okay. Again, I clarify. To calculate volume CSTR, volume PFR, both table and plot pun boleh digunakan. Okay. However, okay, even dalam tutorial nanti dalam test pun I will ask you either guna table or guna plot. Okay, tapi kenapa kita kena tahu plot? Okay, the plot has a specific name, Levenspier plot, because using the plot is an easier way for you to imagine the volume of the reactor. Okay, what do I mean by that? Okay, we go first untuk CSTR. Okay, means kita nak guna plot, okay, untuk kira volume CSTR. Nanti saya akan tunjuk pula contoh menggunakan table. Okay, so imagine now you have the table, okay, then you convert into X versus 1 per minus RA and you plot the graph. Okay, kalau kamu plot graph Levenspier, I come back to the next previous slide. Plot dia akan very standard, you know, the plot will be, because dia 1 per minus RA kan, so plot dia akan sentiasa naik. So the plot will goes up, okay, in tandem with the conversion. Sebab dia 1 per minus RA, kamu kena ingat, kalau dia minus RA dia akan menurun, tapi 1 per minus RA dia akan basically macam menaik. So your plot will have an increase of 1 per minus RA with conversion. Okay, so from this plot, we can actually use to imagine the volume of the CSTR. Okay, what do I mean by that? Okay, if you remember, okay, formula untuk cari CSTR volume, again for one CSTR, meaning this is only if you are talking about using one CSTR to achieve your reaction. Bila dah guna lebih daripada satu CSTR, formula ni dah akan berubah sedikit. So you have to understand that part. Okay. When you are using one single CSTR, if you realize, okay, I taught you the volume is equal to FA0 multiply with X multiply with minus RA. Okay. So now you imagine if I use the plot to calculate the volume, if you realize, okay, Katakanlah conversion kita adalah 0.8, 80%. Okay, katakan dalam information yang kamu dapat, reaction yang kamu nak jalankan ni, kamu punya target conversion 80%. Kita kena ingat masa we're talking about reaction, kita biasanya akan target conversion yang kita nak. How much conversion that we desire. Means, katakan saya nak capai 80% conversion, how big my reactor shall be or how much is the volume if I want to achieve conversion of 80%. Okay. Kalau kamu perasan, katakan saya nak capai conversion 80% and I draw a rectangle across this graph. Okay, yang macam kotak merah ni. Okay, kenapa kotak merah ni kat 0.8? Sebab kita nak target katakan conversion 0.8. Okay, if you realize this red box, if you want to find the area, luas untuk kotak merah ni, the area of this red box, it will be, you have to multiply X, okay, panjang darab sisi, darab tinggi kan. So, the length is X, the height is 1 per minus RA. If I want to measure the area for that red box. So, the area of the red box will be length X multiplied with 1 per minus RA. I will get the area of this red box. So if you connect back to the equation, X multiplied with 1 per minus RA, which is equivalent to the area of the red box. And if you multiply with FA0, you basically get the volume of the CSTR. So in a simpler word, atau you kan plot ni lebih senang untuk kamu imagine. Maksudnya, if you have the plot and you measure the area above and below the curve, dia adalah dia punya curve kan, ni curve dia. Yang kamu kira luas tu adalah luas di bawah curve dan luas di atas curve. So this two area is the luas of the red box, right? Okay. So the area above and below the curve and you multiply with FA0 is equivalent to the volume of the CSTR. Sebab tu dia akan guna graph. Sebab graph tu kamu boleh imagine, okay, saya kira luas bawah dan di atas curve, saya darab dengan FA0, saya dapat volume CSTR. Okay, so that's why kita guna curve, allowance per plot untuk mencari volume CSTR. Okay, let's say you are still not sure. Okay, let us try example. Okay, I give you example guna table, example guna plot. Okay, kamu kena tahu dua-dua cara sebab nanti, again, it depends. Bukan saja sebab test atau sebab exam. It also depends on the information given to you. So, let's say kalau katakan you work in a chemical plant, it depends. If let's say your chemist give in the form of plot, boleh solve. Bagi dalam bentuk table pun boleh solve sebab equation tetap sama. Cara pengiraan saja yang berbeza sedikit. Okay. Now, let's say I'm using a table. Let's say you imagine someone gave you this table of information. Alright, dia kata reaction A to B is carried out in a CSTR. So, it's important when you're solving reaction question, kena tahu reactor apa yang kamu tengah design. Batch ke, PFR ke, CSTR. Now, we're talking about CSTR. Okay. Reactant A enters the reactor at a rate of 0.4 mole per second. Okay. Part ni kamu dah kena tahu starting actually by now you should already have a very good understanding of information ataupun kenapa information tu merujuk kepada apa. Okay. In this case, first dikata enters reactor rate 0.4 mole per second. Okay. Katakan kamu tak sure 0.4 mole per second ni apa? Molar flow rate ke, volumetric flow rate ke, concentration ke, number of moles ke? What is it? Okay, I always tell you, right? I teach you, tengok unit untuk kenal pasti apa information tu. Okay, dalam information ni, kamu tengok the unit is mole per second. Okay. Daripada unit, kamu convert kepada dimension. Mole tu dimension dia mole lah kan? Second dimension dia time. So, kamu tahu mole per time, molar flow rate. Hopefully you should know how to correlate. Kalau mole per time is molar flow rate. How laju molar. How fast my mole in terms of time. Okay, so you know that is molar flow rate F. Okay, so kamu tahu dah F sebab molar flow rate kita guna simbol F. Tapi you have learned molar flow rate spesifik kepada compound kan? Dia compound A ke compound B. Okay, they say in this question reactant A. So of course refers to compound A. So Fa. Tapi Fa ada dua jenis. Fa, Fa0. Why? Fa0 refers to molar flow rate before the reaction occurs. Fa is the molar flow rate of A during or after the reaction. So kamu kena check dia Fe0 ke Fe. So baca balik soalan, dia kata enters the reactor, means dia baru nak masuk dalam reactor. So that will be Fe0. Okay, so tu cabaran soalan engineering tau. Kadang-kadang it's also very normal, right? Meaning, if you work in the real plant, so the person, let's say now your technician is giving you information, the technician will not tell you Fe0 tu sama dengan 0.4. No, the technician also will tell you, okay, the molar flow rate, the initial molar flow rate or molar flow rate asal tindak balas tu 0.4. So you have to be able to catch up, okay, enters the reactor, okay, mole per second, so molar flow rate asal ke, molar flow rate tengah-tengah, molar flow rate akhir. Dia kata enters the reactor, so that is initial molar flow rate, Fe0. So information dia bagi, Fe0 0.4 mole per second. Okay, so they say calculate the volume to achieve 80% conversion in a CSTR using the table. Okay, so information kamu ada, we know the molar flow rate, initial molar flow rate. So kamu imagine sekarang, you have a CSTR, you set the molar flow rate 0.4 mole per second and reaktor kamu tu mesti capai conversion 80% or 0.8. Okay, so 80% conversion dia mesti capai kalau saya nak run molar flow rate saya at 0.4 moles per second. How big my reactor will be? Okay, kita tak tahu berapa besar reaktor kita kalau kita nak mencapai this kind of situation. Okay, so how do we solve it? Okay, so I always teach you, not only for reaction, it's actually for all kinds of engineering. Kamu take your time to process information, especially for reaction. Sebab reaction, katakanlah awal-awal tu kamu dah salah process information, the entire calculation will be wrong. So maksud saya katakan yang 0.4 tu, katakan kamu tersalah, kamu kata dia lah Ce0, confirm dah salah pengiraan. Or kamu kata tu bukan Fe0, Fe, salah pengiraan. So most of the time, student make mistake kat the very first part tu dia dah salah. So first part tu dia dah salah interpret information, entire calculation will definitely be wrong already. So reaction you really need take your time, betul-betul check information. Jangan rushing nak solve problem. Sometimes problem tu senang, tapi salah process information, it become wrong. So a little bit sayang lah, because it's not that you don't understand, you actually do understand, but a little bit of misinterpretation of information. Okay, so I will help you as well as I taught you reaction to help you to actually understand masalah dulu, then only you solve. Okay, so first Fe0 kita dah identify 0.4 mole per second. X, okay, dia kata 80%, don't forget change to fraction. Okay, sebab why I keep reminding, most of the time, mungkin I understand maybe you're doing test, you're doing exam, you already got panic, anxious, so you do all this a little bit of tiny mistakes. So ingat, pengiraan mesti tukar kepada fraction. 80% become 0.8. Okay, next. Minus RA dia. Okay, so kamu tahu kan dalam formula ni, okay, katakan kamu tak sure apa lagi information yang diperlukan. Okay, so this is also a way I teach my student engineering question. Okay, let's say kamu tahu setakat ni kamu hanya boleh digest dua information, Fa0 dengan X. Okay, lepas tu kamu tak sure cukup ke tak nak solve problem ni. Okay, what do I always tell my student? At first identify equation apa yang kita akan guna. Okay, of course pada part setakat ni senanglah, kita baru belajar very limited equation, it's quite easy to know. But okay, you know kamu nak cari volume kan, so volume CSTR kita baru belajar formula dia equals to Fa0x per minus RA. Okay, so you know dalam equation ni I have 4 unknowns. Volume, Fa0, x minus RA. Saya ada 4 unknowns. Okay. First, kamu tahu. Second, kamu identify apa unknown yang kita nak solve. Kita nak solve volume kan? Kita nak tahu volume. Meaning in my equation, only unknown yang volume tu saja yang kita tak tahu dahulu sebab kita nak cari. Okay, so you know in engineering or in mathematics, we call this, you learn in CPP, degree of freedoms analysis. So sometimes students, perhaps we don't really understand why is this important. Okay, degree of freedom analysis kata, okay, kalau kamu ada satu equation, macam contoh ni kamu ada satu equation, kalau kamu nak solve equation tu, kamu kena hanya ada satu unknown saja yang kamu tak tahu. Selebihnya unknown tu kamu mesti tahu dahulu, then you can solve the equation. As long as, let's say you have one equation, you have more than one unknown, katakan ada 2 unknown, confirm sampai besok pun problem tu tak akan dapat solve. One equation, only one unknown. If you have a lot of unknown in the equation, kamu kena cari yang lain tu dulu, baru kamu boleh solve that one unknown that you want to know. As long as you don't have or you don't know the other unknown, you can never solve. Okay, so maybe you have question tapi memang tak boleh cari. Maksudnya katakanlah kamu ada satu equation, kamu dapat tahu yang kamu ada dua unknown. Lagi yang dua-dua ni memang kamu dah tak ada information. So what the way mathematics will do? Meaning kamu kena cari atau find or try to get another one more equation. Meaning dua unknown, dua equation. So kalau katakan kamu ada satu equation, kamu check lagi ada tak lagi equation yang mengkaitkan antara unknown ni. Two unknown, two equation. Three unknown, three equation. So on and so forth. Selagi bilangan unknown lebih daripada equation, kamu takkan dapat solve sampai bila-bila. Okay, so that's one way you to solve not only for reaction, for any other courses that involve engineering calculation, that should be something that you must really remember. Okay, so come back to this. Okay, so come back to this. Means sekarang kita ada satu equation kan? So kita tahu, we know that we want to find volume. Meaning, FA naught, X and minus RA, we have to know first. We don't know these three, we can never find the volume of the CSTR. Okay, so FA naught, we already know 0.4. X 0.8. Okay, what about minus RA? Okay, so kamu kena ingat, you have to know minus RA is if minus RA is reflected by the conversion. Maksudnya daripada table, the table says at 0.8 conversion, 80% conversion, minus RA dia 0.10. Hence, the minus RA will be 0.10 lah. Minus RA when my X is 0.8. So minus RA is 0.10 when my X is 0.8. So my minus RA I replace with 0.10. Okay, you solve the equation. This is the part where I did tell you, kalau kamu nak make sure calculation tu betul, mungkin equation yang senang macam ni, kamu tak buat unit, pembatalan unit pun tak apa, because it's a very easy equation. But sometimes as you go on later, you learn a lot of equation, you can get confused. Okay, so I always encourage you guys to include the unit and do the unit cancellation as you calculate. Okay, contohnya dalam case ni, you can see the mole can be cancelled. Top and bottom, I can cancel the mole. Second, I can cancel as well. I'm left with dm cube. So, 1A per B per C. Kamu tengok ni pun macam pecahan sikit, kamu kena faham lah. A per B per C, dm cube ni kat layer ketiga akan naik ke atas. That's why you get the final unit as dm cube. Okay, so ni a little bit of maths. A per B per C, the third layer punya unit in this case goes to the top. So that's why it become at the top sekarang dm cube. The number value is 3.2. Okay, so why this is important? Come back to what you want to find. You want to find volume, right? Kamu tahu volume, unit dia mestilah unit yang berkaitan dengan volume. So you know dm cube, dimension dia adalah volume. Unit dm cube, dimension, volume. So kamu memang nak kira volume. So most likely, if you get the right unit, most likely your calculations are correct, or most likely you are using the right equation. Sebab kalau guna equation salah, equation yang tak betul, kamu tak akan dapat, most likely kamu tak akan dapat unit yang betul. Okay, so done one calculation using table to find volume. Okay, so next one, kita guna plot pula. Okay, so now we are using the plot to find, okay, cuba tengok soalan dia. Dia kata reaction A to B carry out CSTR. Reactant A enters the reactor rate 0.4. Soalan yang sama kalau kamu perasan, tapi sekarang kita guna plot. Okay, so FA naught dia masih sama 0.4. They ask us to find volume CSTR conversion 80%. So kamu imagine soalan tadi kamu solve dengan table. Next, now you imagine you don't have the table. Now you have the plot. How are we going to solve this if we want to use the plot? So tadi yang table tu information tu kan, dia dah sekarang tukar dalam bentuk plot. Tapi jangan lupa, please don't forget, sebab sometimes student pun terlupa, kalau table is X and minus RA. Kalau plot, X and 1 per minus RA. Jangan lupa, di reciprocal. Dalam plot kita menggunakan reciprocal minus RA. 1 per minus RA. Kalau table kita menggunakan minus RA. Okay, why this is important? Masa part calculation. Okay, what do I mean by that? Okay, so kamu imagine you have the plot. Okay, kamu ingat kan saya ajar kamu kan CSTR, dia punya volume equal to area below and above the curve, or basically the area of the rectangle, multiply with FA0. Okay, so macam nak buat? Volume CSDR sama dengan FA0. Okay, FA0 0.4 multiply with the area, right? So the area will be the length 0.8. The height is 10. Okay, so multiply with 10. Okay, multiply with X 0.8 multiply with 10, the height. Okay, part ni yang kadang-kadang student akan jadi terconfused. Kenapa tiba-tiba darab 10, doktor? Bukan bahagi. Kamu kena ingat, plot ni yang tinggi ni, the height is 1 per minus RA. 1 per minus RA itu adalah 10. Sebab tu kamu darab directly 10, bukan bahagi dengan 10. Kalau tadi table information tu minus RA, sebab tu kamu kena bahagi dengan nilai minus RA. Tapi when you use the plot, nilai tu adalah 1 per minus RA, which is 10. So that's why kamu darab dengan 10. Macam dapat 10. Kamu kena tengok plot ni pada 0.8, okay, 1 per minus RA dia adalah 10. That's why you multiply directly with 10. Okay, let's say kamu tak sure ataupun kamu tak percaya, kamu buat unit pembatalan. FA0 0.4 mole per second. Conversion got no unit, dia fraction kan? Conversion got no unit because in the form of fraction. Multiply with 0.8. Multiply with 1 per minus RA. So 1 per minus RA is 10 dm cube second per mole. Kalau kamu tengok unit 1 per minus RA ini kan terbalik unit minus RA. Kalau unit minus RA, mole per dm cube second. 1 per minus RA terbalik. Jadi dm cube second per mole. So kamu perasan saya cancel mole, I cancel the second, I'm left with dm cube. So you get the same answer, still the same volume. Okay, so this is to help you to understand how to determine the volume. First using table, second using the plot with the aim to still find the volume of CSDR. Okay, so again if you ask, bila nak guna table, bila nak guna plot, it depends on what information are given. Kalau dia dalam bentuk table, gunalah table. Dia dalam bentuk plot, gunalah plot. Either way pun masih jawapan yang sama. Okay, so done on CSDR. CSDR is very easy. Cabaran dia sekarang adalah PFR. Sekejap ni. Now the challenge is you want to calculate for PFR. Okay, why I say it's a challenge? Sama je. PFR, regardless table or plot, you can still calculate the volume. That is correct. Okay, sama je macam CSDR. Guna plot, guna table, you still can find the volume. One. Second, but PFR is harder to calculate because PFR now is an integral equation. Volume PFR kan sama dengan FA0 in bracket, not in bracket, integrating from 0x dx per minus RA. So kamu dah tak boleh solve sebarangan sebab dia sekarang melibatkan integral, pengamiran. Okay, now. But again, I told you plot tu lebih senang untuk kamu imagine area dia. What do I mean? Imagine volume dia. What do I mean? Okay, when you plot the level sphere plot, okay, kamu kena ingat level sphere plot ataupun table, data tu kamu kena ingat dia adalah bergantung kepada tindak balas. Dia tak bergantung kepada volume maksudnya ataupun tak bergantung kepada reaktor maksudnya. Kamu guna batch ke PFR ke CSDR pun table ataupun plot maknanya X melawan minus RA itu is the same for all kinds of reactor or the data of X per minus RA or the level sphere plot is the same regardless what kind of reactor that you use. That data X minus RA, X versus minus RA or the level sphere plot is specific to the reaction, not reactor. Maksudnya kalau kamu menjalankan satu tindak balas, let's say the reaction is called saponification, to do so, right? So as long as you are running the same saponification reaction, data X dengan minus R itu adalah sama, level sphere plot pun sama. Just that kamu akan guna data tu untuk mencari volume yang berlainan. Volume reactor akan berlainan, okay, tapi data information yang digunakan adalah sama. So sebab why I keep clarifying sebab I can understand sometimes student get confused. Apa kaitan, apa benda yang bergantung kepada reactor, apa benda bergantung kepada tindak balas. Okay, so that's to clarify on that part. Okay, back to the lemon sphere plot. Okay, for CSTR, just now I told you, the volume is equal to the area above and below the curve kalau CSTR. However, for PFR, the volume of the reactor, PFR, is actually equal to only area under the curve. So, kalau kamu nampak plot yang dalam slide saya ni, the area under the curve that I'm showing you, this is equal to the volume of your reactor. So, kamu sendiri boleh tengok kan? It's not easy to calculate, right? Nak kira luas ni tak senang kan kalau CSTR luas segi 4. Easy to calculate. But this one is not area under the curve, of which is not that straightforward to count or to determine. Okay, so your question will be then macam mana kita nak kira? Okay, maksudnya again, kalau kamu tengok integral equation ni, yang part dx per minus RA ni, part pengameran ni bersamaan dengan luas di bawah graf. Multiply with FA0. Beza, tadi CSTR luas di atas dan di bawah curve, darab FA0 sama dengan volume CSTR. Okay, so how do we find the area under the curve? Okay, you have already you have definitely learned this in mathematics. I'm not sure what kind of course, I cannot remember the course name, but you have definitely learned in mathematics. Area under the curve of a plot, we have few ways to find. Okay, ada banyak cara sebenarnya, but for our reaction, we use what we call as Simpson's rule. Okay, Simpson rule is a mathematical rule. It's not a chemical engineering rule. It's a mathematical rule yang kamu pernah belajar untuk mencari the area under the curve. And if you still remember, Simpson rule ada banyak jenis kan. We have 1/3, we have 5/7, we have 7/12 method. Apa beza dia? Method 1/3, 5/7, 7/12, different way. This ketiga-tiga pun Simpson rule. Tapi kalau you use 1/3, you have a formula. 5/7 another formula, 7/12 another formula. Okay, kalau you forget, apa beza dia? Okay, beza dia adalah how the way you split the plot. Apa maksud dia? Okay, katakan dalam untuk kita chemical engineering, untuk reaction ni kita guna 1/3, Simpson 1/3 rule. So Simpson 1/3 rule will divide the area under the curve into 3 points. So kalau 5/7 dia akan split kepada 7 point, kalau 7/12 split kepada 12 point. Actually, if you ask me, the bigger the rule means 5/7, 7/12, the calculations are more accurate sebab the more you split luas tu, kamu split kepada bahagian-bahagian kecil, pengiraan dia lebih accurate. Kalau kita guna 1/3, not so accurate, tapi it's okay. So we will use Simpson 1/3 rule is sufficient enough to know the volume. Okay, so maybe if you ask, tepat ke? In terms of reaction, dia punya perbezaan volume kalau kita guna 1/3, 5/7, 7/12, the difference in the volume is not significant. So it's fine to just use 1/3 rule. Okay, so now kita akan guna Simpson 1/3 rule to find the area under the curve, and then subsequently kita guna untuk cari volume CSTR. So now volume PFR, sorry. So now you can see why I keep telling you reaction engineering is a close correlation between mathematics and chemistry. Bagaimana kita solve engineering question, reaction engineering questions, but we are using maths principle. Okay, so now I come back to teach you Simpson 1/3 rule. Okay, from the equation, again, you are not expected to memorize the equation. Memang in my reaction engineering, my style, you don't need to memorize equations. Sebab we are very practical. When you join the working world, you can always Google. It's just a Google away from finding the equation. However, the focus in this course will be how are you going to able to apply the equation. Sebab as I told you, reaction very diverse. Saya boleh tukar just one parameter, equation tu dah. Kamu dah tahu nak apply dalam equation. So, fahamkan how to use the equation. No need to worry on the memorization. Okay, right. So the volume of the PFR equals to FA naught integrating 0x dx per minus RA. Again, why? Bottom limit dia kosong sebab dalam single PFR, conversion pada asal mesti kosong. Maksudnya belum apa-apa lagi A di-convertkan. Upper limit final conversion, X. Okay, kan saya dah kata yang integral part ni akan kita solve using Simpson one-third rule. Sebab kita dah establish yang part integral ni bersamaan dengan luas di bawah curve, area under the curve. So, since integral part equals to area under the curve, I solve the area under the curve using Simpson one-third rule. Okay. So maksudnya part yang depan FA0 ni masih ada. Jangan lupa FA0 tu ada. Okay. Now let me teach you the back part. How we get the Simpson one-third rule punya formula. Okay. So kamu dah kena faham formula design tu, formula volume PFR tu becomes a Simpson one-third rule multiply with FA0. Okay, FA0. Okay. In bracket delta X per 3. I will teach you later apa maksud delta X per 3. Just remember delta X. Yang segitiga tu means delta X over 3. Then I will explain later what's that. Okay, then behind bracket, a big bracket, you have 3 points. Sebab one-third rule, 3 points. Kalau 5, 7 rule ada 7 point, 7, 12 ada 12 point. Okay, so now one-third rule nasib baik, kamu ada 3 point. Sebab tu ada 3 data. Okay, the first one is 1 per minus RA at my lower limit of X, which is 0. Sebab pengambilan saya bermula daripada kosong. Hence, the first point is 1 per minus RA when my X is 0. Ataupun dalam bahasa Melayu, my 1 per minus RA apabila X saya kosong. Bukan darab dengan X, dia hanya nak signify sebab minus RA kan bergantung kepada X. So kita nak dapat minus RA apabila X saya kosong. Okay, so first I go to the back first. Nanti saya explain yang bahagian tengah. Saya pergi ke belakang dulu. Yang ke belakang is 1 per minus RA at my final X. Apa tu final X? Tengok apa limit pengambilan saya. Saya ambil daripada 0 to X. So the first point just now, minus RA when my X is 0 kan. 1 per minus RA when my X is 0. The last point, 1 per minus RA at my X. So katakan your final conversion is at 0.8. So di sana maksudnya 1 per minus RA apabila X saya 0.8. So kamu tengok table ataupun kamu tengok plot. Okay, tengok pada 0.8 ni berapa minus RA saya. Ataupun pada 0.8 ni berapa 1 per minus RA saya. You get the last point. Okay, so first and third kamu dah faham. I go to the middle one. Okay, the middle one, the number is 4. Formula dia dah one-third rule-nya formula 141. So 4 tu stays. Formula Simpson one-third rule. Dia memang saya tak boleh explain in terms of engineering. In terms of mathematics, dia kata letak 4. So it's a 4 over 4 per minus RA at my middle X. 4 ni yang kamu akan confuse sikit. Dia kata 4 per minus RA at my middle X. What do I mean by middle X? Okay, ni kamu kena cari sendiri. Kamu kena tahu sendiri berapa middle X saya. Maksudnya, katakan asal bottom limit 0, right? Lower limit 0. Katakan upper limit kamu adalah 0.8. Katakan you're integrating from 0 to 8. So my bottom is 0. My upper X is 0.8. Hence, my middle X will be 0 to 0.8. Middle X saya adalah 0.4. So, it become 4 per minus RA when my X is 0.4. Okay, again I repeat, middle X you have to find yourself. Basically, titik X yang tengah-tengah di antara bottom lower limit dengan upper limit. Okay, example lagi. Let's say your X is, your final X is 0.6. So, 0 to 0.6, middle X kamu 0.3. So, become 4 per minus RA when my X 0.3. Okay, that's how to find your middle X. You have to actually find by yourself. Kira titik tengah. Okay, done on the bracket. Let me go to the delta X per 3. Okay, part ni kamu kena betul-betul faham. Okay, dia kata delta X. I hope you understand. Kalau kamu perasan, delta tu maksud dia julat. Okay, delta tu maksudnya gap. The gap different, or dalam bahasa Melayu kita panggil julat. The easiest way to understand is julat or the gap of difference. Okay, apa gap dia tu apa? After the difference tu difference apa? Okay, is the gap or the difference in the difference between ataupun nilai julat di antara bottom limit, lower limit to your middle X or your middle X to your final X. Kalau kamu perasan, kalau X middle X kamu betul, the difference between X0 to X middle and X middle to X is still the same kan, dia punya julat kan. Maksud dia apa? Okay, katakan your X, your beginning is 0, your final X is 0.8. Hence, your middle X 0.4 kan. So, delta X will be either 0.4 minus 0, still 0.4. Or, kalau kamu nak guna yang belakang, 0.8 minus 0.4 masih juga 0.4. So, your delta X is 0.4. Okay, again, then after that, divide by 3. Kenapa 3? Again, Simpson one-third rule. One-third rule, that's why dia bahagi dengan 3. Okay, now I have to clarify on the delta X. Okay, maybe at this point, you think, you assume, which is actually correct at this situation, delta X ni macam sama dengan middle X. Betul, sebab contohnya katakan kamu guna, tadi yang saya bagi contoh, 0, 0, 0.4, 0.8. Delta X 0.4. Depan belakang pun 0.4. Mungkin kamu kata bukan sama dengan middle X ke? When it is the case of single reactor and kamu punya permulaan start dengan 0, it is correct. Gap tu sama dengan nilai middle X. It is correct bila it involves single CSTR dan kamu bermula dengan X 0. Single punya reaktor mesti bermula conversion daripada 0. However, dia akan menjadi confusion kemudian when we learn reactor in series. Sebab bila reactor in series, kita akan kira volume, kita akan guna formula ni. Formula sama. Tetapi, when kita nak calculate series punya reactor volume, let's say the reactor is second in series or third in the series, permulaan conversion tu bukan 0. Dia akan start daripada conversion yang telah dicapai pada reaktor yang awal. So, it can be yang initial conversion tu maybe 0.6. Katakan kamu imagine initial conversion 0.6, final conversion 0.8, middle conversion dia 0.7, delta X dia 0.1 if you realize. So, you understand yang delta X tu bukan, kalau dia single reactor, yes, is equal to the middle conversion, but in a reactor of series, dia dah tak sama. So you have to understand actually the concept of the delta X, which is I want to emphasize. Delta X tu adalah julat atau perbezaan or the difference between initial X to the middle X or middle X to your final X. Okay, then you divide by 3. Right, okay, done on this information. Okay, so let's say we give an example, kita nak cari, kita bagi example. Jadi example ni saya dah explain tapi mungkin dalam bentuk equation is better. Okay, now you imagine I want to find the volume of a PFR with my conversion 0.8. Okay, 0.8 punya conversion. So volume PFR equals to FA0 integrating 0 to 0.8 dx per minus RA. So again, why bottom limit, lower limit 0? Sebab single PFR, dia start conversion daripada 0 to your final conversion, let's say 80%, 0.8. So you have to rewrite back in the form of Simpson one-third rule. So beginning FA0, in bracket delta X per 3, okay. So that in bracket, okay. So I always advise my student to do this supaya kamu akan faham. Bottom limit 0, upper limit 0.8. Find your middle x 0.4. Okay, kamu tahu middle x tu 0.4. Delta x dia adalah gap tu. So the gap will be depan atau belakang pun kamu kira gap dia adalah sama. Meaning if you find at the front, delta x dia will be 0.4 minus 0, 0.4. You find at the back, 0.8 minus 0.4, still 0.4. Okay, so delta x is 0.4 over 3. In bracket, okay, 1 per minus RA when my x is 0, 1 per minus RA apabila x saya kosong, because that's the bottom limit, plus 4 per minus RA at my middle x, which is 0.4. So middle x tu yang kamu kena cari sendiri. So kamu kena tahu apakah titik tengah antara 0 dan 0.8, which is 0.4. Plus 1 per minus RA when my x at my final conversion, 0.8. So when you have the information from the table or the plot, you can solve this equation. Okay, so kamu kena ingat, PFR susah sikit sebab kalau tadi CSDR terus solve directly, PFR kamu kena convert kepada Simpson one-third rule baru kamu solve. Okay, so let us try to solve the same question tapi tadi CSDR, now is a PFR. Okay, so dia kata still reaction A to B. Okay, initial molar flow rate dia FA0 is still 0.4. Okay, FA0 0.4 sama macam CSDR tadi. They ask us to find volume to achieve 80% conversion in a PFR using the table. So kita buat macam tadi CSDR, tapi sekarang kita nak cari, we want to find the volume of a PFR using this table. So table ni kamu kena faham. Okay, again I repeat. So maksudnya from this table, when my x is 0.1 minus RA dia 0.44. When my x 0.2 minus RA dia 0.42. So on and so forth. Okay, how to find the volume? Okay, so again, in process dulu information kita ada two information which is FA0 dan X. Okay, so then volume PFR equals to FA0 integrating 0 to 0.8. Make sure kamu tulis dengan betul dahulu your bottom limit and your upper limit supaya kamu tahu permulaan X dan pengakhiran X. dx per minus RA equals to FA0 delta X per 3 in bracket 1 per minus RA when my X is 0. So kamu kena check. Bila X saya kosong, 1 per minus, bila X saya kosong, minus RA saya 0.45. Kamu kena ingat kan, kalau guna table, information dia X minus RA. So when my X is 0, my minus RA 0.45. Next, plus 4 per minus RA when my X 0.4. Ingat dia bukan darat, dia hanya untuk tunjuk berapa nilai minus RA saya apabila X saya 0.4. So from the table, when my X 0.4, my minus RA 0.32. Next, 1 per minus RA when my X 0.8. So when my X 0.8, minus RA 0.10. So you replace into the equation. So FA0 0.4, delta X kira tadi kita dah buat kan. So delta X 0.4 juga over 3 in bracket you replace at 0 0.45. So 1 per 0.45 plus 4 per 0.32. Kenapa 0.32? Sebab dia kata minus RA apabila X saya 0.4. At 0.4 minus RA saya 0.32. Last one, 1 per minus RA when my X 0.8. So pada 0.8 X minus RA saya 0.10. So solve, don't forget table adalah minus RA. Kamu kena ingat tak, kadang saya keep reminding ni, bukanlah sebab saya apa, sebab these are the very normal mistakes yang student buat yang saya rasa sayang sebab sebenarnya student faham je tapi mungkin dia terconfuse sikit ataupun sebab dia dah banyak sangat benda dia jadi confused. Sebab tu keep remind supaya kamu akan somehow remember don't do these mistakes. Okay, so then you replace As I always tell you, I will do unit cancellation. You cancel the unit. You should get the correct unit. Kalau kamu dapat unit yang betul, most likely your answer is correct. So we get 1.32 dm cube. Apa maksud volume ni? Maksud dia, kalau kamu ada molar flow rate A kamu 0.4, kamu nak mencapai conversion 80%, untuk tindak balas yang dalam table ni, reaktor kamu punya volume kecil je, 1.32 dm cube je. It's about 1 liter, 1.32 liter, which is quite small reactor. That's the meaning. What are you calculating right now actually? Okay. So next one, okay, after this example, I will give a little bit of break. Okay, sebab saya tahu dah quite heavy sikit. Okay, so now you want to solve back the same thing using plot. Okay, so tadi kita solve guna table kan. Now kita nak solve benda yang sama, exactly the same thing, but we are using the plot. Okay, so kamu ingat kalau menggunakan plot maksudnya is equivalent to the area under the curve. Okay, tapi sama je. Kita masih menggunakan Levenspiel plot. Tapi kamu kena ingat part yang sangat saya keep reminding, kalau table kamu guna minus RA. If you are using plot, it is 1 per minus RA. Maksudnya, okay, kalau kamu tengok, layer pertama penyelesaian saya sama kan? Kita guna formula yang sama. But when you want to replace the value, you have to be very careful. Why? Okay, first FA0, 0.4 as given by the question. Your delta X is still the same, sama je, because again, kalau conversion dia, the conversion is the same, right? So the conversion is the same. The delta X will still be the same because it's the gap between first initial X to the middle X or middle X to the final X. So regardless, you calculate delta X at the front or delta X at the back, the gap is still the same, which is 0.4. You divide by 3. The formula says you have to divide by 3. However, in that bracket, that 3 point ni, you have to be very careful. Why? Because first, it's 1 per minus RA when my X is 0. Okay, you look. When my X is 0, my 1 per minus RA, this is about 2.22. Tak apa, nanti if in the exam or test, I will give you correctly the number so that you don't have to guess. Okay, so at 0, my 1 per minus RA is 2.22, this point. That's why you replace directly with 2.22 sebab dia adalah 1 per minus RA when my X is 0. Next, 4 per minus RA when my X 0.4. Maksudnya if in the plot at 0.4, my 1 per minus RA, this point is actually 3.13. Okay, so of course at this moment kita macam nak nampak. Okay, kalau dalam test atau exam, I will give you the number untuk setiap point tu supaya kamu tak confused. But basically this point is 3.13, 1 per minus RA dia. That's why you multiply 3.13 multiply with 4. Don't forget, student always forget to multiply the 4. 4 tu ada, so dalam formula dia 4. So 4 multiply with 1 per minus RA when my X 0.4, which is 3.13. Plus, last one, when my X 0.8, my 1 per minus RA, this one is 10. So become plus 10. Terus tambah 10 sebab dia adalah 1 per minus RA when my X 0.8. So when you solve this, you will and definitely get the same final answer. Is still 1.32 dm3. So kamu kena faham. Table ke, plot ke, as long as you are using the same information, you will get the same final answer. Okay? Alright, so that's all for right now. Okay, bukan lebih kas lagi. I will give you about 5-minute break. Okay, just take a break a little bit. You will come back about 10:40. So you got about 7-minute breaks and then we come back in 10:40 to continue the lesson. Okay, alright. Okay, so we will continue a little bit more. So I think about, I will continue a little bit more, maybe about 30 minutes, then we are done for today class. All right. Okay, so we will try another kind of question. So kita dah, actually we already learned how to find the volume of PFR and CSTR using a table or using a Levenspiel plot. Okay, so let's try another question. So this is here. Reaction A and B is carried out in 100 dm cube PFR or 100 dm cube CSTR. Okay, so you imagine now, let's say in your plant, you already have an existing reactor. So kamu kena faham juga, when we are solving questions, when I teach you how to solve the question, we also have to imagine different scenario in your chemical plant. Okay, so of course, the ideally apa kita buat adalah, okay, we know a reaction, we have the data, we know the volume of the reactor, kita design reactor yang baru, kita beli reactor tu. Okay, but you know, right, in a plant, very rarely, unless your plant is a new plant and you're going to start up, you baru nak start up plant tu, possible lah, you get to purchase a new reactor. But you know, reactor is very, very expensive, definitely. So most of the time, if you're working in an existing chemical plant, very rarely you get to buy new reactor. Most of the time, kamu kena adjust ataupun kamu kena recalculate or readjust parameter to fit to an existing reactor. Maksudnya, macam tadi kita kira, kita nak tahu volume. Kalau kita tahu conversion, kita tahu molar flow rate. Okay. Now you imagine a scenario of which saya dah ada reactor tu. Means in your plant now, you have two PFR, you have either, you have a PFR or you have a CSTR, both of which the volume is 100 dm cube. This one besar lah, 100 dm cube is about 100 liters. It's a huge reactor. And dia kata sekarang, calculate the initial molar flow rate, which is A lah, for both reactor. Okay, kenapa saya tahu molar flow rate A? Sebab reactor dia hanya satu, A. Okay, so dia nak tahu molar flow rate A for both reactor to achieve 60% conversion using the table. So kamu imagine sekarang, I have the reactor, I have these two reactor, I know the target conversion is 60%. I need to calculate what are the molar flow rate that I need. Okay, so kamu imagine sekarang dalam plant tu dah ada reactor, saya dah tahu conversion saya nak capai, saya kena manipulate ataupun saya kena kira balik berapa molar flow rate A yang saya kena guna if I want to achieve these both conditions. So these questions are more relevant to existing reactor and just molar flow rate. So something kamu kena ingat, katakan sebelum ni kamu, let's say you have a new reaction, so on and so forth, kamu dah ada reactor yang sedia ada, kamu kena adjust parameter. So in this case, kita kena kira, we have to calculate the molar flow rate to achieve that condition. Okay, so on your left hand side is using for is calculating for CSTR. Your right hand side is calculating for PFR. So kamu boleh tengok CSTR is straightforward lah kan. Okay, let us do again the same question. So in this question, dia nak cari FA0. Okay, so what do you do? Okay, first, as I taught you for solving engineering question, cari dulu equation. Apa equation kamu nak guna? Okay, so you know so far, you just learn satu equation je kan, dua equation. So not so difficult lah. Kalau CSTR, basically this equation, volume CSTR equals to FA0X per minus RA. Okay, you know, the target unknown that you want to calculate is FA0. Maksudnya, the other unknowns tu dah kena tahu dulu. You need to know volume, you need to know X, you need to know minus RA. Without these three unknown, you cannot find your FA0. Okay, so they told you the reactor volume was 100. Okay, so settle. Left hand side, settle. My volume is 100 dm cube. FA0, I want to find. My X, they say like the conversion is 60%. My X, desired X is 0.6. So X 0.6. At the bottom, my minus RA when my X is 0.6. So when my X 0.6, my minus RA from the table is 0.17. So you divide by 0.17. Okay, you're left with FA0. So as I always told you, try to do unit cancellation. So you can see kalau saya buat unit cancellation, I can only cancel dm cube. I'm left with mole per second. Okay, so that thing again, you want to calculate initial molar flow rate of A. So molar flow rate, mole per time. Mole per time, unit dia katakan mole per second. You get mole per second, betul lah? Mole per second is mole per time. So correct dimension, correct unit, most likely your answer is correct. So when you are using CSTR, if your volume reactor is 100 dm cube and you want to achieve 60% conversion, you have to control your molar flow rate of A at 28.33 mol per second. Means kamu kena adjust, kamu nak pump molar flow rate tu, kamu kena adjust pada 28.33. Then only you can achieve conversion 60% in 100 liter CSTR. Okay. Now let us calculate untuk PFR pula. Okay. So for PFR, same different formula, design equation dia, FA0 integrating 0 to 0.6. So why 0.6? Because the initial conversion 0, the final conversion targeted is 0.6 dx per minus RA. Change to Simpson one-third rule, so automatic. Okay, bila question yang melibatkan table atau plot, volume CSTR, you have to convert into the Simpson one-third rule. So become FA0. Okay, so FA0, saya terus pergi ke line kedua. FA0 is what you want to find. So FA0 remains. Okay, volume kita tahu sama. PFR volume desired is also 100. So left hand side is still 100. FA0 remains. Then delta X per 3. So delta X per 3 again, if I will do this form of table, this form of calculation. So initial bottom limit 0, upper limit 0.6, middle X, my middle between these two are 0.3. Hence, my gap, my delta X will be either 0.3 minus 0, which is also 0.3, or kalau nak kira X, gap, delta X at the back, 0.6 minus 0.3, also delta X 0.3. So delta X 0.3 divided by 3. Kenapa bagi 3? Simpson wanted rule kata divide by 3. So divide by 3. Then the 3 points in the bracket. So the first one, 1 per minus RA. When my X 0, because my bottom limit is 0. So when my X is 0, my minus RA is 0.45. So 1 per 0.45 plus 4 per minus RA at my middle X, which is 0.3. So at 0.3, my minus RA is 0.37. So 4 per 0.37. Last, 1 per minus RA when my X at my final X 0.6. From table at 0.6, my minus RA 0.17. So 1 divided by 0.17 are the unit dm cube second per mole. Sebab unit dia kan 1 per minus RA. So unit minus RA ni kamu terbalikkan. Sebab tu jadi dm cube second per mole. When you cancel dm cube, you will still get your final answer mole per second, but your FA0 is now 52.87. So if you realize, walaupun you're using the same table, kamu perasan kan CSTR PFR, kita guna table yang sama, betul untuk pengiraan. Tapi kamu perasan walaupun volume dia sama, the volume are the same, even the conversion the same, but the molar flow rate is actually different. Sebab tu kamu kena kira pengiraan ni, sebab design equation berbeza, that's why you get the molar flow rate different. Apa maksud dia? Maksudnya, if you want to achieve, you have reactor 100 liter, PFR or CSTR, achieving 60% conversion, the molar flow rate needed for CSTR is 28.33, but for PFR, you need 52.87, a bigger molar flow rate for you to achieve the same conversion in comparison to your CSTR. So you can have you understand the significance of walaupun volume reactor sama, conversion sama, tindak balas sama, kamu punya nilai akhir tu takkan sama sebab design equation dia adalah berlainan. Okay, alright. So we do again, okay, kita tukar sikit soalan, sekarang kita guna plot pula. Okay, so why I keep doing this practice is again to help you as well as nanti kita akan pergi reaktor bersiri. Nanti pergi reaktor bersiri tu kamu akan start jadi pening kalau kamu tak faham yang single reactor. So I explain first single reactor until you faham, then I can go to the reactor in series easier. Okay, so reaction, the next example, A to B carry out reactor volume both PFR, CSTR, tapi sekarang reactor volume dia 200 dm3. So lebih besar reaktor dia sekarang, 200 dm3. They ask us to calculate again FA0. Okay, sama juga calculate FA0 untuk PFR, FA0 for CSTR to achieve complete conversion of A using the plot. Okay, tadi kita guna table, achieve 60% conversion. Now kita guna plot, okay, and volume reactor dia 200 each, and dia kata achieve complete conversion. So what do you mean by complete conversion? Maksudnya, in a simpler words, all of my A is converted into B, or in terms of X, it means 100% X, or in terms of fraction, 1. So, berapa molar flow rate kalau saya nak capai complete conversion? X1 for these reactors of when we use plot. Okay, so again, kita buat benda yang sama. Okay, so plot ni, I already give you the point punya value, so it's easier for you to calculate. Okay. We do first for CSTR. Okay, so CSTR volume equals to, again, FA0X per minus RA. FA0 is the one that we want to find. Okay, so kamu kena faham. Tadi contoh yang sebelum-sebelum ni, kita cari volume. Contoh ni, kita dah tahu volume. Okay, so dalam case yang practically means, katakan dalam plant tu, kita dah ada volume, kita dah ada reactor tu, kita kena adjust molar flow rate. Okay, so FA0 is what we want to find. So the volume 200, left hand side settle, right hand side FA0 we want to find, so we let it be, multiply with X, so dikatakan nak achieve complete conversion, so X is 1. So jangan lupa complete conversion 100%, tapi dalam penyeraan tukar jadi 1 fraction. Okay, multiply with, pada when my X is 1, my 1 per minus RA is 12.99. So kamu kena ingat, kalau plot, apabila X1, 1 per minus RA dia adalah 12.99. So you multiply directly with 12.99. Jangan dy. So kamu kena faham. Tadi kalau kita buat table, nilai dia minus RA. Sebab tu kita bahagi dengan minus RA. Kita guna plot is already 1 per minus RA. Dia dah reciprocalkan nilai tu. Sebab tu kita darab terus dengan 12.99. So you calculate, you get your FA0 15.4. Okay, now go to PFR. So PFR volume kita dah tahu 200 equals to FA0. We want to find integrating from 0 to 1. So kenapa sekarang 0 to 1? Sebab single PFR from 0 conversion to final conversion 1. dx per minus RE. Okay, so kita solve this. Okay, so left hand side 200 volume. Right hand side FA0 I leave it because I want to calculate, right? Okay, delta X. So delta X ni kamu kena fikir. Okay, saya tak buat yang the gap, but you can imagine kita integrating from 0 to 1. So my bottom limit 0, my upper limit 1. So my middle X, the middle X will be 0.5. X tengah, middle dia 0.5. So delta X dia adalah gap between 0 to 0.5 or 0.5 to 1. So kalau kita kira gap di depan, 0.5 minus 0, 0.5. You kira gap at the back, 1 minus 0.5 is also 0.5. So delta X dia 0.5. So again, I repeat, delta X is not your middle X. Just that, kalau case single PFR, yes, okay, so happen. Tapi kemudian bila pergi reaktor bersiri, kamu akan faham kenapa delta X tu bukan middle X. Okay, so then divide by 3 in bracket 1 per minus RA at my bottom limit 0. So when my X is 0, my 1 per minus RA is 2.22. Okay, so 2.22 plus 4 per minus RA at my middle X, which is 0.5. So at 0.5, my middle, my 1 per minus RA is 4. So jangan lupa 4 darab 4. Why 4 times 4 is 4 per minus RA when my X 0.5. So 4 multiply 4. Tengah ni yang biasa student terlupa nak darab dengan 4. Sebab dia lupa yang ada 4 dalam equation tu. Plus 1 per minus RA when my X is 1. So when my X is 1 from the plot, 1 per minus RA dia adalah 12.99. So 12.99. So kamu imagine, kalau in artikel lain, kamu dia kira nilai area ni kan berdasarkan area pertama, area kedua. Sebenarnya dia pecah 3 point, dia kira area pertama, area kedua. So kamu akan nampak it's not so accurate. But as I told you, the volume is not so impacted by the difference of the area. So when you recalculate this, you get the molar flow rate as 38.45 mole per second. So that's how you can see sama volume. Kamu kena perasan juga sama conversion, sama plot. It's actually the same plot, but you get two different molar flow rate because of the you are using different type of reactor. Okay, so kamu kena faham part tu, perbezaan tu disebabkan kamu menggunakan pengiraan yang berlainan, design equation yang berlainan, so the calculation will give you different outcome. Okay, so finally we are done with reactor, one reactor, single reactor for PFR, single reactor for CSTR. Okay. Now we come to the harder part. Okay, so saya masuk sikit je, nanti saya sambung lagi pada minggu depan. I just go in a little bit, then next week I will go in deeper just to explain one part of the equation first. Okay, tadi yang what you did baru je ni, you're calculating volume single PFR, single CSTR. But I did told you that in the problem with when you're using single reactor ni adalah, let's say you don't achieve high conversion, means tak banyak A kamu yang di-convert. Of course, ideally, if all your A's are converted in one reactor, senanglah settle, tak ada masalah. Tapi very rarely that occurs. Sebab tu, they will use catalytic reactor. Kalau conversion dia terlalu rendah, dia akan guna catalytic reactor, ditambah catalyst. Or another way, as I told you, either dah keluar daripada the single reactor, separate or purify first, and then recycle my unconverted reactant. That's one way. Or second way, you could actually connect it to the next reactor. Okay, so dengan harapan after the first reactor, let's say conversion tak tinggi, so you have a mixture of unconverted A, katakanlah A menghasilkan B kan, so kamu ada the mixture of A and B. So you know A is money, because unconverted reactant are a waste in the system. So you flow directly from the first reactor, the mixture of A and B, you flow directly to the second reactor. It's still an open system, flow in, flow out, with the hope that in the second reactor, yang baki A tu akan bertindak balas lagi untuk menghasilkan lebih banyak B. That's one scenario when you have less conversion in the first reactor. One reason why you use reactor in series. Second reason is sometimes, okay, let's say you are working with existing reactor. Okay, let's say now when you calculate, okay, sometimes let's say you calculate untuk satu single reactor kan, kata kamu nak capai 80% conversion, kamu kira-kira katakan reactor volume tu, katakanlah it must be 10 liter. Okay, maknanya kalau nak capai conversion 80%, molar flow rate ni, reaktor yang diperlukan mesti at least 10 liter. Okay. Then, tapi when you propose to your boss say kita tak boleh beli reaktor. We have no money, we cannot purchase reactor, you can only use the existing reactor. Means kamu tak boleh beli reaktor baru, means tapi dia suruh kamu guna existing reactor. Okay. Then bila kamu check reaktor yang dalam plant tu, there's no reactor of 10 liter. Let's say ada 5 liter, ada a few reactors of 5 liter, let's say. So you must understand, if you cannot run in a 10 liter reactor, you can actually break down the reaction using several smaller reactor, meaning to achieve that 80% conversion, of which you need a single 10 liter reactor, you may run the same reaction, achieving the same conversion using maybe 2 or 3 or more reactors of a smaller volume in series. So this is also something that you have to understand engineering wise. Tak semesti kena guna satu reaktor nak achieve conversion yang kamu nak. Kamu boleh guna reaktor yang lebih kecil, but you connect it in series, you can use more than one reactor. So let's say ada baki, macam I told you the situation, you have smaller reactor, let's say you have more than one, you may actually use that reactor configuration in series to achieve the same outcome. So That of course kamu kena ingat jugalah, mungkin kamu kata adakah lebih murah, lebih mahal, you have to consider. Sebab kalau nak guna reactor in series, sama je lah, kamu kena consider pump, kamu kena consider a few factors. But most of the time, connecting reactors in series, smaller ones, if you have existing one, are way cheaper than purchasing a new reactor, for sure. Okay, so that's one alternative why you have to learn reactor in series, and because it is quite common industry as well to use reactor in series. Okay, so back to this. Okay, so now the challenge in using reactor in series, kamu kena faham a few concept. Okay, first of all, concept dia, it is an open system, meaning our flow in from the first reactor will continuously flow, the outflow of the first reactor is also the inflow for the second reactor, and so on. Okay, dalam contoh saya saja kamu 2, tapi kamu kena dalam industri tak semestinya 2, can be more than 2. Okay, dan kamu kena faham, in series reactor, kamu dah tak kacau apa-apa dalam sistem tau. Maksudnya, molar flow rate yang kamu manipulate only at the very beginning. Means feed molar flow rate FA0 tu, let's say kamu adjust at 10 mol per second. Itulah 10 mol per second akan guna untuk semua reaktor. Kamu dah tak kacau part yang lain. Sebab dia akan mengalir keluar masuk pada reaktor kedua. Reaktor kedua punya molar flow rate tu kamu dah tak kacau. Kamu hanya kacau pada reaktor pertama yang kamu adjust tu. Itulah molar flow rate untuk keseluruhan tindak balas. Meaning at second reactor you do not disturb the molar flow rate. Subsequently you do not disturb the molar flow rate. You just let it happen. First thing. Sebab tu FA0 akan sentiasa merujuk kepada FA0 always refers to the initial molar flow rate at the very first reactor, or the molar flow rate yang kamu prepare tu yang kamu boleh control, FA0. Means kamu nak tukar 10, kamu nak tukar 15, kamu prepare tu kamu boleh tukar, you can adjust, manipulate FA0. Okay. Then we have FA1. What is FA1? FA1 is the outlet molar flow rate of reactor 1, which is also the inlet molar flow rate to the reactor 2. Kamu kena ingat yang mengalir keluar reaktor 1 adalah juga yang mengalir masuk kepada reaktor kedua, FA1. So FA1 you cannot manipulate, you cannot control, you cannot adjust. Tu dah termaktub sebab kamu tak kacau sistem untuk FA1. Subsequently, FA2 okay, adalah molar flow rate that exits the second reactor, which is also the inflow to the third reactor. So kamu ada FA2, FA3, so on and so forth. So next concept, FA1 definitely lebih kecil daripada FA0. FA1 will definitely be smaller than FA0. Why? Sebab FA0 tu kan molar flow rate E. Dalam reaktor pertama mesti dia akan consume, right? Dia akan di-converted. So FA1 smaller than FA0. Naturally, FA2 smaller than FA1 sebab FA1 katakan asal 100 mol per second of E. After first reactor, katakan baki 80 mol per second of A. Masuk reaktor kedua, FA2 60 mol per second, so on and so forth. So FA1 smaller than FA0, FA2 smaller than FA1 sebab as it goes through reactor, it will be converted, it will be consumed. So kenapa saya beritahu ni? Sebab let's say you are calculating FA1, kamu kira FA1, kamu perasan nilai FA1 tu is bigger than FA0. Katakan FA0 kamu kira 10, suddenly FA1 kamu dapat 12. So you know logically, if you remember chemical engineering, tak mungkin sebab FA1 kan dah consume, mana boleh nilai FA1 lebih besar daripada FA0. So you know you already make a mistake. Check back calculation. So most of the time engineering, not necessary reaction, all kind of engineering question, kalau apply logic, most of the time you know your mistakes. If you remember to apply certain logics to it. Okay, so this is one example. Kamu tahu FA1 tak mungkin lebih besar daripada FA0. You get a bigger value, recheck calculation, confirm dah salah at any part. Okay, next. Okay, done on FA, right? Done on the molar flow rate. Next, conversion. Okay, conversion ni pun kamu kena ingat. Konsep yang kamu kena ingat juga. Okay, conversion at before it enters the reactor, of course, conversion A tu kosong kan? Okay, so conversion A tu kosong. After it goes through reactor 1, certain A will be converted, right? Okay, conversion akan meningkat. Conversion akan meningkat dengan reactor. Kenapa? Sebab The more reactor it travels, the more A will be converted. So conversion akan meningkat. Okay, kenapa conversion meningkat? Kalau kami ingat, conversion kan sama dengan berapa yang telah bertindak balas terhadap berapa yang saya swap. How much reacted over how much I fed. So naturally, with more reactor, more A will react. So conversion will increase with the number of reactor. So maksudnya, okay, let's say reaktor pertama FA0 100. FA1 let's say 50. Okay lah, saya kata 60 lah senang 60 mol. So conversion reaktor pertama 100 minus 60 bahagi dengan 100 is 40%. Okay, 100 tolak 60 bahagi 100, 40%. Meaning dalam reaktor pertama 40% A telah converted. Betul kan? Sebab 100 mol jadi 60 mol, 40 mol hilang kan? 40% lah. Okay, hilang 40%. Means conversion dah 40%. Okay. Then, second reactor, kamu kena ingat, yang tadi masuk kepada reaktor kedua masih 60 mol. Bukan 100 mol. Sebab dia kan sambungan, dia just baki kan? 100, 60 masuk reaktor kedua. Dia bukan, FA1 ni bukan 100 balik. Dah 60. Okay. So 60 masuk dalam reaktor kedua. Let's say dia convert lagi 20. Okay, maknanya 20 telah convert. Let's say sekarang FA2 tu baki 40. Let's say, so means 100 mol, 60 mol, FA2 40 mol. Okay, sekarang berapa conversion dia? Conversion dia akan menjadi, kamu kena kira pada asal 100 tolak dengan 40 bahagi dengan 100, dia jadi berapa persen? 60%. Maksudnya, reaktor pertama conversion daripada 0 kepada 40%, 0 to 40%. The conversion in the second reactor is now increased to 60%. Kenapa 60%? Daripada 100 jadi 60 jadi 40. So conversion will increase with the number of your reactor. Maksudnya X1 will be, X2 bigger than X1, X3 will be bigger than X2, so on and so forth. So logik lah, sebab tadi saya beritahu pasal FA1 kan, saya kata FA1 akan jadi lebih kecil. Kalau FA1 jadi lebih kecil, maksudnya lebih banyak bertindak balas. Lebih banyak bertindak balas, maksudnya conversion akan meningkat. So dia songsang, dia reciprocal one another. FA1, FA2 has to be smaller and then only the conversion will increase. Okay, so that's on the conversion. Maksudnya conversion, yang erti kata lain, conversion tak reset. What do you mean by this? Because students already got confused pasal conversion ni. Okay, reaktor pertama sebab kita kira berdasarkan 100 asal yang masuk. Okay, so in the first reactor dia akan convert, as I told you, from 0 conversion kepada 40% conversion. Okay, then masuk pada reaktor kedua tu conversion bukan start balik pada kosong. Conversion tu start daripada yang asal daripada reaktor pertama yang telah kamu capai, which is 40%. Sebab kita kira baki yang 60 tu, yang baki reaktor pertama tu masuk pada reaktor kedua. So the conversion in second reactor naturally from 40% to 60%. So let's say if you think it's still low, you go to the next reactor, you hope that from 60% goes to 100% or 80%, so on and so forth. So with each reactor, conversion akan meningkat until finally all of my A has been converted in the reaction. Okay, so that's one thing. Okay, next. Untuk setiap X ni, of course ada minus RA dia. So means in reactor pertama at X1 minus RA1. Katakan your conversion is at first reactor 50%. So minus RA when my X 0.5. Let's say reaktor kedua conversion kamu meningkat kepada 0.8. So minus RA at X 0.8. Okay, now so you have X1, X2. So sometimes you get confused macam kita nak panggil. Katakan kita ada 10 reaktor. Jadi kita nak bezakan conversion tu. Okay. The conversion from the first until to the for the second last reactor, kita panggil intermediate conversion. The conversion at the final reactor is the final conversion. Maksudnya katakan kamu ada 3 reactor, the conversion X1, X2 is called intermediate conversion X3 is the final conversion. If I have 10 reactor, 1 to 9 intermediate conversion, at 10 reactor is the final conversion. Okay, right. Now that I've done explaining it, now saya kena explain pula bagaimana formula conversion dah berubah. Sebab tu tadi saya explain tu, bukannya apa? Bukannya saya cerita sebab explanation tu to help you understand equation conversion. Sekarang equation conversion jadi a little bit memeningkan kepala. Sebab tu kamu kena faham konsep dan kamu akan faham equation. Okay, now kita nak kira conversion X1, X2, X3. So, formula yang sebelum ni kamu belajar, kamu dah pernah belajar kan? Saya dah ajar kamu conversion asal formula yang saya ajar. X equal to FA0 minus FA per FA0. Means yang kalau single reactor, FA0 yang masuk minus FA yang keluar bahagi balik dengan FA0. Sebab konsep dia yang telah bertindak balas terhadap berapa yang saya swap. Okay, now conversion tu kita kena bahagikan kepada pengiraan yang berbeza. Because let's say now I have 3 reactor. I have 3 different conversion kan. X1, X2, X3. So ketiga-tiga ni formula conversion dia dah berubah sedikit. So how does it change? Okay, so first reactor, kamu imagine first CSTR kamu, okay. Let's say CSTR atau PFR pun sama je. Okay, before I forget, formula conversion ni sama je. Nak guna untuk PFR ke, nak guna untuk CSTR ke, formula conversion dia adalah menggunakan pemahaman yang sama. Okay, design equation berlainan, tapi part conversion pemahaman yang sama. Sebab conversion tu bergantung kepada molar flow rate A. Kamu guna PFR ke, CSTR ke, molar flow rate A, konsep dia, pemahaman dia masih sama. Okay, so for the first reactor, conversion X1 equals to enters the reactor FA0. Sama je kan macam yang equation asal. But now dia minus FA1. Kenapa FA1? Sebab FA1 adalah molar flow rate that exits the first reactor divided with FA0. Bila kamu rearrange balik equation ni, sebab bila kamu rearrange, kamu akan faham lebih senang. Bila kamu rearrange, kamu akan dapat FA1, molar flow rate that exits the first reactor equals to FA0 in bracket 1 minus X1. X1 is the intermediate conversion in the very first reactor. Okay, kalau kamu tak nampak ni, kamu kena rearrange sikit lah, mathematics sikit. Okay, kamu akan dapat dalam bentuk FA1 equals to FA0 1 minus X1. Okay, tak apa. Reaktor pertama biasa memang saya tahu student takkan confuse. The confusion comes at second reactor. Okay, second reactor kamu kena faham. Okay, I want to find conversion at second reactor. So X2 dah sekarang. Okay, sama dengan FA0. Okay, part ni yang kadang student a bit confused. Kenapa bukan FA1? Kenapa kita kira FA0 walaupun yang masuk ke dalam reaktor kedua adalah FA1. Tapi kamu tengok conversion saya kira guna FA0. Sebab yang saya beritahu kamu kena ingat bilangan mol tu, molar flow rate tu dia berterusan. Dia maksudnya dalam reaktor pertama, saya katakan dalam reaktor pertama, katakan 100 mol per second yang masuk reaktor pertama. A kan, FA0 tu 100. After dia keluar reaktor kedua tu, katakan baki 60. Okay, kamu kena faham, conversion ni mesti berdasarkan yang asal yang masuk pada reaktor pertama. Sebab reaktor pertama yang masuk tu, yang asal yang kamu prepare tu 100. We are calculating conversion from that raw ataupun from that molar flow rate yang kamu prepare pada waktu asal tu. Means 100 mol tu, kita nak tahu berapa peratusan sampai dia convert habis 100 mol. So that's why pengiraan untuk reaktor kedua, dia masih yang masuk adalah FA0. Asal liquid yang kamu prepare ataupun asal gas yang kamu prepare, berapa molar flow rate dia, molar flow rate tu lah kamu kira untuk dia punya conversion. So that's why saya katakan kamu, conversion tak reset. Conversion takkan reaktor kedua tu bukan start balik pada kosong. Dia bersambung daripada yang tadi mula daripada reaktor pertama. Means reaktor pertama conversion 40%, reaktor kedua tu akan naik daripada 40% kepada 60%. Kenapa dia boleh naik? Sebab saya kira berdasarkan FA0 yang asal. Okay, so that's why it become FA0 minus minus FA2 yang keluar daripada reaktor yang kedua. So imagine 100 mol FA0, FA1 60, FA2 40. So 100 minus 40 bahagi dengan 100, you get 60%. So reaktor pertama katakan 40%, reaktor kedua naik lagi conversion kepada 60%. So when you rearrange, you get Fa2 equals to Fa0 in bracket 1 minus X2. Okay, so that's for reaktor kedua. And for the third reactor, okay, same concept. Okay, katakan kamu ada 3 reaktor. Reaktor ketiga, conversion dia X3 equals to, again, the very initial molar flow rate Fa0 minus molar flow rate exits the third reactor Fa3 divide by Fa0. You get Fa3, the outlet molar flow rate of the third reactor, as Fa0 in bracket 1 minus X3. Okay, now kalau kamu perasan, kamu nampak there's a correlation kan? Kalau reaktor pertama, Fa1, Fa0, 1 minus X1. Fa2, reaktor kedua, Fa2, Fa0, 1 minus X2. Reaktor ketiga, Fa3, Fa0, 1 minus X3. So katakan kalau reaktor keempat, it become Fa4 equals to Fa0 in bracket 1 minus X4. Let's say you have 10 reactor, F10. Fa10, maknanya outlet molar flow rate of A pada reaktor ke-10 at the 10 reactor equals to Fa0 in bracket 1 minus X10. So kamu dah boleh agak formula dia, even I don't show you, you can see, you can predict the formula for the next subsequent reactors. Okay, one. Second, as I told you, conversion tak reset. Dia akan meningkat dengan bilangan reaktor. So katakan reaktor pertama from 0% to 30%. Reaktor kedua yang masuk daripada 30% menjadi let's say 50%. Reaktor ketiga from 50% to let's say 70%. Reaktor keempat from 70% to finally 100%. So dia conversion tu akan meningkat. Dia tak reset sebab we calculate the conversion based on the very initial molar flow rate yang masuk itu. So sebagai example 100 daripada 100 tu yang kita kira conversion untuk setiap reaktor. Sebab tu dia akan meningkat. Okay, so conversion with subsequent reactor will and must increase. So let's say, kenapa saya keep reminding this, let's say kamu buat calculation, you calculate your X3. Okay, let's say you calculate your X3, you dapat X3 tu katakan 80%. Okay, let's say 50% X3, then when you calculate X2, you dapat 70%. So, kamu tahu mesti salah, takkan daripada 70% A, masuk reaktor kedua, reaktor seterusnya terus turun kepada 50%. Tak boleh sebab conversion will continuously increase. So, there's also a way for you to check your calculation. In conversion, increase with your number of your reactors. Okay. Alright, so I will stop at this point sebab kalau saya nak pergi kepada design reactor punya calculation, you will get a little bit more confused. So, sekarang kamu dah nampak kan, conversion punya equation pun dah berubah sebab bilangan reaktor. Nanti when we talk about design reactor pun akan berubah equation dia. So that part yang a little bit confused. So I don't want to touch for today. I will continue on next Monday. Okay, so next week lecture and tutorial as usual. Lab kita akan start pada minggu ke-4. So the following week. So should be 17 March baru kita start lab. Okay, minggu depan tak ada lab lagi tapi I will release the schedule next week for the lab one. Okay, don't worry. Okay, for those yang ada balik about lab physical, you're worried about the pandemic and so on, I already have a very good strategy. Okay, I make sure we will use 2 labs. Kalau kamu perasan lab 7, lab 8 tu besar. So instead of using 1 lab, saya pecah guna 2 lab. And saya restrict the time. So instead of 3 jam setiap lab, saya restrict kepada 90 minit sahaja. So kita akan habis lab dalam masa 2 minggu. So 2 lab besar, you got about 9 person in 1 lab, another 9 person, 2 groups. Saya pecahkan dari 4 group sahaja, yang datang hanya 18, 4 group. I pecah to 2 labs, so 1 lab about 9 student, in the lab 9 student. I shorten the experiment time so that you can do more experiment. You can finish the entire experiment in 2 weeks, and if you take care of our SOP, I can tak boleh cakap surely lah, I will make sure that our safety is taken care lah during the lab, but not next week, the following week. Okay, so that's all for today. Please have a little bit break before you go to your next class. If you have questions, you can also ask me now, or if you're a little bit shy, you can just text me after the class. Okay, so thank you everyone for today's class.